Hello everyone. Once again I welcome you all to MSB lecture series on interpretative spectroscopy. In my last lecture I was discussing about spin-spin splitting. So that means often when we run NMR spectrum for a molecule, we see not a single line, and a single line consists of many lines with different heights, that means different intensity. Why that happens? So that I started discussion on that one. Let me continue from where I had stopped. As I mentioned, another useful property that allows NMR spectra to give structural information is called spin-spin coupling, which is very important, and it's very vital in understanding and diagnosing the molecule while elucidating its structure, which is caused by spin coupling between NMR active nuclei. You should remember NMR active nuclei that are not chemically identical. Different spin states interact through chemical bonds in a molecule to give rise to this coupling. That means if we have two carbon atoms are connected by a bond or two, in that case protons present on both the carbon atoms interact, provided they are in different chemical environment. In NMR spectra, this effect is shown through peak splitting that can give direct information concerning the connectivity of atoms in a molecule. Not only that one, and also they can precisely tell you how many protons are there, equivalent protons are there on the carbon, the adjacent carbon atom. Nuclei which share the same chemical shift do not form splitting peaks in an NMR spectra. This is very important. Nuclei which share the same chemical shift do not form splitting peaks in an NMR spectra. In general, neighboring NMR active nuclei 3 or fewer bonds away leads to this coupling. In special cases, even if they are 4 to 5 bonds away, they can still interact and influence in splitting the signal. The splitting is described by the relationship wherein neighboring nuclei results in N+1 peaks. That means if we have n number of proton atoms are there on adjacent carbon atom, that leads to the splitting of the adjacent one by N+1 peaks. If 3 CH2 are there, then in CH2, so for example 2 are there, then it will make the neighboring one into 3. If 3 are there, then it appears as 4, something like that. And that information directly comes from Pascal triangle for a particular I value. So you should remember Pascal triangle will be varies with I values. I equals half, we have a different Pascal triangle. I equals 1, we have a different Pascal triangle, and we have to use a totally different Pascal triangle when I equals 3/2 or 5/2. So however, being adjacent to a strongly electronegative group such as oxygen, that can prevent spin-spin coupling between two neighboring groups where we have protons. For example, a doublet would have 2 peaks with intensity ratio of 1:1, while a quadret would have 4 peaks, a relative intensity of 1:3:3:1, or if you have a triplet, the relative intensity will be 1:2:1. So the magnitude of the observed spin splitting depends on many factors and is given by the coupling constant J, which is in units of hertz. So when we see this triplet, quadret or doublet, the spacing between the two lines, we call it as coupling constant J. It is always represented in units of hertz. Also, we get information about peak intensity. So the size of the peaks in the NMR spectra can give information concerning the number of nuclei that give rise to that peak. So this is done by measuring the peak area using integration. That information again comes from NMR spectra, yet even without using integration, the size of different peaks can still give relative information about the number of nuclei. Even if you don't have that integration, simply by looking into the height of the peaks, we should be able to judge. But sometimes it can be misleading, and we should not just go by the height. Sometimes what happens if the broader one, the height is small, that can occupy more larger area, and still that can be having considerable peak height. So one should be very careful about that one. and it is better to integrate rather than looking into the height to decide the intensity. For example, a singlet associated with 3 hydrogen atoms would be about 3 times larger than a singlet associated with a single hydrogen atom. What are the limitations of NMR then? Despite its ability, there are several limitations that can make NMR analysis difficult or impossible in certain situations. One such is that the desired isotope and element that is needed for NMR analysis may have little or no natural abundance. For example, I am interested in a particular isotope of a nuclei which is NMR active, but that may be in very insignificant quantity in the natural resources. So that means, for example, if you consider the natural abundance of 13C, the active isotope for carbon NMR with I equals half is about 1.1%, whereas the rest is 12 carbon, which is NMR inactive because I value is 0. Still, 1.1% is quite sufficient to plot 13C NMR and look into NMR spectrum, and it can still help to great extent in elucidating the structure and getting lot of information. However, in case of oxygen, the active isotope for NMR is 17 oxygen, which is only 0.035% naturally abundant. This means that there are certain elements that can essentially never be measured through NMR. So no matter how much quantity we take, it is very difficult to identify and run 17O NMR spectra for a molecule where we have insignificant quantity of 17O isotope. So that means in case if you want to run 17O NMR, it has to be enriched. So another problem is that some elements have an extremely low magnetic moment. That means the sensitivity is very, very low. So the sensitivity of NMR machines is based on the magnetic moment of the specific element, but if the magnetic moment is too low, it can be very difficult to obtain NMR spectra with enough peak intensity to properly analyze. So these are the limitations of NMR. One is less abundance and another one is the low magnetic moment value. What are the basis for spin coupling? Well, already I discussed some of those in a couple of slides earlier, but let me go back again and repeat some of these facts so that understanding would be much better. So NMR signals arise when nuclei absorb a certain radio frequency and are excited from one spin state to another one. So this, whatever the energy we are supplying is equal to the normal frequency of this one, then flipping of this one takes, and that we call it as electronic transition. And the exact frequency of electromagnetic radiation that the nucleus absorbs depends on the magnetic environment around the nucleus. So that means whether it's given nucleus is shielded or de-shielded also should be considered. This magnetic environment is controlled mostly by the applied field, but is also affected by the magnetic moments of nearby nuclei. So nuclei can be in one of many spin states, giving rise to several possible magnetic environments for the observed nucleus to resonate in. So this causes the NMR signal for a nucleus to show up as a multiple or multiplet rather than a single peak. So because of the interference of magnetic field generated by neighboring nuclei, what happens, the signals will be split into multiplets, 1, 2, 3 or 4 depending upon the magnitude of the field, and also number of such nuclei that are generating induced magnetic field. In NMR experiments, only nuclei with I equals non-zero will show up in NMR spectrum. Again, I am telling you. So when I equals 0, there is only one possible spin state, and hence nucleus cannot flip between states. So why? So it has only one state, so that it cannot flip. Since the NMR signal is based on the absorption of radio frequency and the nucleus transition from one spin state to another one, plus half to minus half, or 1 to minus 1. I equals 0 nuclei neither show up NMR nor cause splitting of other NMR signals because they only have one possible magnetic moment. This simplifies NMR spectra. In fact, this also comes very handy in simplifying the NMR spectra, in particular of organic and organometallic compounds, greatly, since the majority of carbon atoms are 12 carbon which have I equals 0 value. We have to consider only 1.1% of 13C that has I equals half value. So here I have given a typical spectrum here, chloroethane, and you can see here we have a triplet of 1:2:1 intensity and we have a quartet of 1:3:3:1 intensity for these methylene protons and a triplet for methyl protons. How we get triplet here and how we get quartet here, I will show you after a couple of slides. So now for a nucleus to cause splitting, it must be close enough to the nucleus being observed to affect its magnetic environment. For example, if a particular group, protons present on a particular group are influencing the splitting, they should be on the adjacent carbon atom, or at least they should not be beyond 3 or 4 bonds. That's what it means. The splitting technically occurs through bonds, and often we can also come across through space coupling also. That I would take up at the end. So here the splitting technically occurs through bonds, not through space. So as a general rule, only nuclei separated by 3 or 4 bonds can split each other. However, even if a nucleus is close enough to another, it may not cause splitting. For splitting to occur, the nuclei must also be non-equivalent. So they must be non-equivalent. As I mentioned, in case of ethane, we have CH3 group and CH3 group are there, and both the CH3 groups are not splitting each other because both are chemically equivalent. That means there must be some non-equivalence there to split the neighboring signals. To see how these factors affect real NMR spectra, consider the spectrum for chloroethane here. There are 2 groups of peaks in the spectrum, as I mentioned, a triplet and a quadret. These arise from the 2 different types of I equals non-zero nuclei in the molecule. Yes, the protons on the methyl and methylene groups, the multiplet corresponding to CH3 proton appears as a relative integration. The peak area comes here of 3, 1 for each proton, and is split by the 2 methyl protons N equals 2, which results in N+1 peaks, that is 3, which is a triplet. So the multiplet corresponding to CH2 protons has an integration of 1 for each proton and is split by 3 methyl protons N equals 3, which results from N+1 peaks, that is 4 peaks, which is a quadret, and each group of nucleus splits the other. So in this way they are coupled. That means both are coupled here, and if you measure the spacing between the lines here and the lines here, that is similar. The spacing what we call between the 2 lines in a chemical shift is called coupling constant and is represented in Hertz. To see how these factors affect real NMR spectra, again I am considering this chloroethane. There are 2 groups of peaks in the spectrum, a triplet and a quartet. I am just repeating again. These arise from the 2 different types of I equals non-zero nuclei in the molecule, the protons on the methyl and protons on the methylene group. The multiplet corresponding to methyl protons has a relative integration of 3 for each proton and is split by 2 methylene groups, protons N equals 2, which results from N+1 peaks here. N+1 peaks are coming because of CH2, 2 plus 1, 3, which is a triplet, and the intensity ratio is 1:2:1. The multiplet corresponding to CH2 has an integration of 2. This entire integration corresponds to 2 protons, but it is split into 4 with a intensity ratio of 1:3:3:1 because of N+1 coming from here. 3 are there, 3 plus 1, 4. So these methyl protons are split this into quadret, methylene protons are split this into triplet. That's what it is. So now let us consider now 1,1,2 dibromoethane here. The protons on adjacent carbon are non-equivalent. So why this doublet and a triplet? So that means this one shows a triplet, whereas these 2 show a doublet here. So how that happens? Let us look into it, and then values are given here. You can see 4.26, 4.26, this one. These 2 are showing a doublet here, whereas at 6 point centered at 6.51. For this one, we give only one value, the middle one we are giving. Or if you have 5 peaks, the middle one we are taking, and if 6 peaks are between 3 and 4, we take the center point of this one, and it is represented as chemical shift, and here chemical shift is 6.51. So now we have to see why this is doublet and why this is a triplet in a more. Let's first look into this HA signal, HA. So first this is split by these 2 into triplet. How we will see? So now basically what happens? So if you just see here, we have 2 protons are here now. So these protons, both the protons, the magnetic field generated by both the protons can be aligned with the magnetic field. This is more towards the shielded region, and then in this case what happens, one can be upward, one can be downward. This is one possibility. Okay, so we can also have this kind of orientation. If you represent this 1 and 2 and 1 and 2, 1 and 2 both are upwards and 1 is up and 2 is down, and now 1 can be down and 2 can be up. This is another possibility. And then we cannot have any other possibilities. Now the third one will be something like this, 1 and 2. So that means now if you just see, these two are degenerate. So this is one set and this is two set and this is one set. So this is how the signal due to HA appears as a triplet, something like this. Something like this. This is for HA. So now let's look into HB. HB signal we have to see. So HB signal, so now these two will be split based on the magnetic field generated with this one. So now one can be something like this, only one is there, or one can be something like this, only two possibilities are there. As a result, what happens? Either this one can influence its chemical shift. As a result, what happens? It will come little bit de-shielded, and this one will be little bit shielded. So we get two peaks, two lines of equal intensity. So this is how the splitting can be seen, and overall one can write something like this. Something like this, and this, whatever the spacing is there, these spacings are identical. So this we call it as J, and if here if you see 1, 2, 3, so this we call it as 3 J H H. Okay, even if you want to be more precise, you can say that one. So this is how, this is a superscript and this is subscript, and this should be in italic. This is how the coupling constant is presented. This is italic. And then here you see the bond separation, and here the coupled nuclei HA, HB. So this is how a typical coupling constant is represented. So now what is this N+1 rule? So if a signal is split by N equivalent protons, it splits into N+1 peaks. That means the relative peak intensities of symmetric multiplets of first order, and then whatever this Pascal triangle that predicts number of peaks with I equals half, it is very unique for this one, and also this holds good only for first order spectrum. That means if I say first order spectrum, that means something else can also be there. Yes, that is called second order spectrum. Second order will be totally different. So that I shall discuss after completing about first order spectrum and looking into more examples. So if in a typical first order spectrum, and if the I value is half, then we can use very effectively this Pascal triangle. For example, when number of equivalent protons causing splitting is 0, if we have nothing, then only singlet will be observed, because N+1 N is 0, so only 1 will be there, and if only 1 is there, then we will see N+1, 2 lines will be there in 1:1 ratio, and if we have 2 neighboring protons are there, they cause this one into a triplet, then intensity will be 1:2:1, and then if 3 are there, we get a quadret, that is 1:3:3:1, and then if 4 are there, quintet, we get 1:4:6:4:1 ratio, and then if 5 are there, then N+1 will be sextet, we get 6 lines, the relative intensities are 1:5:10:10:5:1, and then if 6 lines are there, we get a septet, then intensity ratio will be 1:6:15, 20, 15, 6 and 1. So this is how, even simply if you name 1, second one can be written, and then you just 1, do this 2 and this 1, and next 1, these 2 3 and these 2 3 and this 1 1. So you should be able to write, once you know only this one, there is no need to remember this one. Next one you can write 1 4 6 4 1, you can write here, and next one is 1 5 and then 10 and then 10 and 5 1, you should be able to write. So now it's 1 is there, 6 is there, and then 15 is there, and then this is 20, and then again 15 is there and 6 is there. So you can keep on writing like that. So once we know up to here, extrapolating that one and writing for higher number of lines should be very easy using this Pascal triangle. So using this Pascal triangle, we should be able to predict the number of peaks, and this equals I equals half. And another equation we use is Ni plus 1. So then if you do not know, or if you have different I values, still this can also be used here. And eventually it will, if you take half is there, for example 2, okay, N again is half plus 1, this will cancel. That's the reason we simplify it and use N plus 1 peaks. So this Pascal triangle is for I equals half value. Similarly, when I equals 1 is there, it changes. And now if you see, for example, if we have 0 nuclei which are influencing, still we get N plus 1, we get 1 peak. And then when we have 1, we get 3 peaks because N plus 1. Here we have to use 2Ni plus 1. 2Ni plus 1 we should use. I is the value. 2 into, if say 1 is there, and then this is 1 plus 1. I value is 1. I value what we are considering is 1. We get 3 lines. Okay, this is what is there. And if 2 are there, 2 into 2 plus 1, so we get 5. This is how you can calculate. And if 3 are there, 3 into 2 plus 1, so we get 7 lines. So you should be able to calculate. So it 5, 11 and 6, 30, and this is the corresponding intensity ratio for number of peaks. It goes like this. So this is this Pascal triangles holds good for those nuclei which have I equals 1 value. Now I have written another Pascal triangle for I equals 3 by 2. For example, if we are using say 11 boron, okay, is I equals 3 by 2, and if we come across any spectrum and if we have more number of lines, we can conveniently use this Pascal triangle to calculate the relative intensities. So here again, if you simply take 0, so here what happens, 2 Ni plus 1. So then of course 0 means it becomes only 1. If you have 1 is there, then 2 into 1 into 3 by 2 plus 1. So we get 4 lines here. 4 lines are there. What would happen if 2 are there? 2 into 2 into 3 by 2 plus 1. So it becomes 7 lines. 7 will be there. And similarly, if you go for 3 here, 3 into 2 into 3 by 2 plus 1. So we'll get 3 into 3, 9 plus 1, 10 lines. So 10 will be there. And similarly, you can go for 4, we get 13. So that means if 4 equivalent nuclei with I equals 3 by 2 are splitting, then 13 lines will be there, and the corresponding intensity will be this one. We have some rough idea about coupling constants. What we have to understand is equivalent protons do not split each other. So that means if you consider a CH3, CH2, OH, and these are equivalent protons, they do not couple each other. That means if I expand them, okay, we write like this. These are all geminal. Okay, that means when they are equivalent, when they are geminal, coupling is not observed in first order spectrum. That's what it is. Equivalent protons do not split each other. And then protons bonded to the same carbon atom will split each other if they are not equivalent due to unsymmetrical nature of the molecule. Due to some reason, if the 2 hydrogen atoms present on a carbon are non-equivalent because of unsymmetry present in the molecule, or molecule is differently substituted on both the ends, in that case what happens, geminal coupling can be observed. In that case, invariably we come across second order spectrum. So protons on adjacent carbon atoms normally will couple. So always the protons on adjacent carbon atoms, provided they are not chemically equivalent, they normally couple. Protons separated by 4 or more bonds will not couple or show very weak coupling. That means to see very effective coupling, they should not be more than 3 bonds apart. If they are more than 3 bonds apart, we may or may not observe coupling, and in case if we observe coupling, the magnitude of the coupling is very small and hence that is very weak. Considering more examples and discuss more interesting aspects about coupling constant in my next lecture. Until then, have a good time. Thank you.